Hello YouTube, this is part 6 of how to build a Raytracer from scratch in C++. Last time we added a couple of classes, the plane class and the sphere class, and we talked a little bit about how Raytracers need to find the intersections between rays coming from the camera and objects within our scene. So we wrote a linear algebra equation find the intersection between rays and planes, and we didn't quite get to doing the same thing for spheres. But today what we're going to do is we're going to start creating rays from our camera as we loop through our nested for loops that run from the top left of the image to the bottom right of the image. So each time we go through a pixel, we're going to start creating a ray and sending it out into our scene and seeing if it intersects with something. We're going to define a few new variables. X amount and Y amount are values that are going to be slightly to the left and slightly to the right of the direction we pointed our camera, which was at the origin. That's in a case without anti-aliasing. We're going to start no anti-aliasing. compile, make sure we don't have any errors. So what we've done is we've created a few variables, we've modified them as we go through according to the height and width of the image and the position that we're at in the loop. And what that's going to do is it's going to offset a position from our direction that our camera is pointed in order to create rays that go to the left of the direction the camera is pointed and rays that go to the right that the direction the camera is pointed, and above the direction the camera is pointed and below. So that there's an image plane in front of the camera, and those vectors, or those rays, they need to go to the left and up and to the right and down of the direction that the camera is pointed in order to cover that image plane. So now we can start creating rays. We're going to let the origin for all our rays be the same as the origin of the camera. So, vect. This get camera position method function returns the camera's origin. So these x amount and y amount values, these are specific to the x and y coordinates that are currently at the variable. At this point in the loop, we're at a specific x and y position in the image plane. So the camera direction that goes through that point is going to be a little bit of linear algebra. But it depends on the camera direction. We can create a new instance of array. where this ray, cam ray, is going through this specific XY pixel into the scene to look for intersections with objects. Let's compile. Good. Now that we have rays, we're going to start sending them into our scene and looking for intersections. So we're going to create an array of intersections. So this is how you define a vector or array, whatever you want to call it, in C++. That's going to hold our intersection values. But one thing that I forgot to do is we need to stack our scene objects so that we can index them and loop through our objects in our scene so that we can have as many objects in our scene as we want. We need to put them in an array as well. This is how we push the objects in our scene into that vector. So now what we want to do is we want to loop through. At this point in our for loops, we're at a specific pixel, and what we want to do is we want to loop through each of the objects in our scene and determine if the ray that we just created intersects with any of those objects in our scene. So what this does is it loops through each object in our scene. It asks to find the intersection with the cam ray. Then it wants to push that value into this intersections vector. The only thing that we can find intersections with right now is with planes, so we'll have to add a class to find we'll have to add a method function to find intersections with spheres, which is unfortunately a little bit more complicated. Let's see what happens when we compile. Good. We're going to go to our sphere class and new method function. Also need to add the getNormalAt method function. So our find intersection function returns a scalar value, which is the distance from the origin of the ray to the point of intersection. Then we can use linear algebra to find the xyz coordinates of that point of intersection and find the normal off of the surface of a sphere at that coordinate. That's how we find the normal of the surface of a sphere. After I find some variables. So we need to get the information from the ray that was being passed to our find intersection function. We need to know the specific x, y, and z coordinates. Direction. we're finding the intersection with the sphere, which is an instance of a sphere. So we need to get the properties of the sphere. We already defined in this instance of the class. It's just the center. These are the A's and B's that correspond to the same A's and B's in the find intersection of the plane class, but they're different for sphere. Value. lot of you probably recognize that in linear algebra. Finally, we can say that if the discriminant is greater than 0, ray intersects the sphere. But if the ray intersects the sphere, it could intersect it on two sides. It could intersect it on one side of the sphere and intersect it on the other side of the sphere. So we're going to have two roots, and there's going to be one of those roots is going to be closer to the camera, and that's going to be the root that is the intersection point. The first root. This 001 number is arbitrary. It helps with dealing with accuracy errors when running through millions of linear algebra computations for some reason. If that root is positive, means that the first root is the smallest positive root. Where we're returning root 1 as the return value for our find intersection function. However, if root 1 is not greater than 1, then the second root is the smallest positive root. And we want to return root 2. In the case where the discriminant is not greater than 0, this means that the ray missed the sphere. And we return -1 as a value that we can use to determine if our ray misses our object. So now we have a find intersection method function for our sphere class, and we can find intersections between rays and spheres. Let's compile, make sure we don't have any errors. So good. So, we started off by offsetting values from the direction that our camera was pointed, and then creating rays that go off in those slightly different directions. So it's different directions about the camera direction. And those rays go off into our scene and check through each object in our scene and look to see if there are any intersections with those objects. And if we find any intersections, we put it in our intersection array. And now what we need to do is we need to see which object is closer to the camera. So we're going to have to create another function that is the winning object in the array of intersections. Where winning object index is a function that we have to create. And that function simply sorts our array of intersections and returns the index of the winning object. And that will be the same index as in our scene objects index, so we know whether the ray intersected the sphere or the plane first. But first we need to create our winning object index function. This is going to be a new function in between our save bitmap function and our main function. It's going to return an integer value. The name of the function is winning object index, which expects a vector of indices, or intersections, I mean. One thing I hadn't really talked about yet was that in Raytracers, we're only worried about the rays that actually intersect with our scene. So we're not worried about rays that bounce off and go in the middle of nowhere. So typically, rays of light originate at the light source, go to the object, and then find their way to the camera. But many rays would be created that way that would cause unnecessary calculations. So if we're having millions of calculations, we want to prevent as many unnecessary calculations as possible. And that's the reason why we start by creating rays at the camera. This is saying if there are no intersections, so we're saying if there were no intersections in the intersections vector to be passed to our winning object index function, then we return a -1, so that means there were no intersections. Else, if there's only one intersection, then we want to check to see make some notes here to say what these are. So, in this case, 0 is not the value of the intersection. 0 is the index of the value in our vector array. So we have an array of values, of intersections. The index of the winning intersection in that vector is the first intersection, which is the 0th element in our vector. So we return 0 because 0 is the winning object index. So if the intersection value that is the only intersection is greater than 0, then that's the winning object, which index is the 0th element. Otherwise, the only intersection is negative. Which means that all of the values in our intersection function, or our intersection array, all those values, if those were negative, that means the ray missed everything. And if there are more than one intersections in the array, we need to determine which one is the least value, or the closest to the camera. So we're going to find the maximum value in the vector. So objects intersections dot size is the number of objects, or the number of intersections in our vector. So we're going to loop through each intersection, and remember there could be dozens of objects in our scene. So if we wanted, we could have 10, 20 spheres, 4 or 5 planes, and each one of those intersects with rays coming through each pixel. So there could be many intersections in general. We want to find which intersection is the closest to the camera because we want the color of that object to be the color of the pixel. So we go through the intersections. If the first one we encounter is greater than 0, then we say that's our max, or the maximum in the array. We don't know that yet, of course, but you have to start somewhere. So we've looped through the objects. We've determined that if there's an intersection that's greater than our maximum value, then we reset the maximum value to the new value, and therefore the smallest positive number, which is what we want to return, is the the index of the number that's less than or equal to the maximum. So we return the index of minimum value. And we still have to deal with the case where if the maximum value was not greater than 0, we want to return -1, because that means all the intersections were negative. Let's compile. Good. So what we have is a ray tracer that creates spheres and planes. Then we put those in a vector, loop through all the pixels in the image, loop through the vector of objects, determine if the rays coming from the camera intersect with those objects, and then determine which object was closer to the camera. Then we can go down here, back into our main function, and now we have a value here, index of winning object. So that's the object that was closest to the camera. That's the object we want to get the color of in order to return that to the color of that individual X and Y pixel. And directly beneath that you'll see the code that we wrote before that generates the image of the square, the maroon square. So next time we'll incorporate this index of winning object feature in order to actually find the color of the sphere or the plane at each individual pixel in the image. That'll be next time. Thanks for watching.